Time runs out in small, decisive slices. 3i Atlas moves inward. The object defies the rules you learned about comets. Instead of recoiling from the sun, this visitor aims its gas at the star. The motion reads like provocation. The star that sustains your world receives the thrust as a deliberate act. Experts stopped arguing about classification. They moved on to survival. Under closed doors, conversations shifted from curiosity to contingency. If this visitor awakens something hidden inside the sun, the fallout reaches cities, supply lines, satellites, and hospitals. The stakes extend beyond laboratory papers and telescope logs. The stakes include daily life. If this mystery grips you, hold on. Subscribe. Follow the updates. Share the thread. Tell others where you watch from and what your clock reads. Spread the signal through social channels or whisper it into your circles. That way the community grows. The community helps parse ambiguity, pressure institutions, and demand transparency. Now, the image. An image arrived that should not exist under current understanding. The picture shows what appears to be a comet firing a jet of gas toward the sun. Toward the star. Not away. Your intuition rebels. Comets point tails away from the sun. They behave like wind socks caught in a stellar gale. Sunlight and the solar wind push material outward. Yet the jet in the image aims inward. Call the object 3i Atlas. The label matters only for tracking and for the fiction of distance. This object did not form here. Astronomers flagged its path as hyperbolic the moment telescopes captured sufficient data. The speed measured near 58 to 60 kilometers per second relative to the Sun. That velocity exceeds bound orbits. The object will pass through, then retreat to interstellar dark. Imagine a scientist who spent decades studying comets. Now picture that person staring at the image. Every rule in textbooks collapses for a moment. The mind tests for error. Perhaps the angle misleads. Perhaps a dust illusion skews perspective. Perhaps a software artifact flipped orientation. Observers repeated the images. Multiple instruments returned the same strange feature. The jet persisted. The James Webb Space Telescope pivoted its infrared gaze toward 3i Atlas. Hubble tracked visible detail. Ground observatories on different continents trained higher apertures on the visitor nightly. Online speculation exploded. Amateur circles and fringe forums raced ahead of peer review. Mainstream astrophysicists published careful notes. Some voices preferred natural explanations. Others opened the door to engineered origins. Ask the simple question, what if the visitor does something to the Sun? No impact risk exists for Earth in terms of collision. No bunkers need immediate stocking. Perihelion will place the object at roughly 1.36 to 1.4 astronomical units from the Sun. That lies outside Earth's orbit in simple geometry. Closest approach between Earth and the object sits near 1.8 astronomical units. Still distant. Collision absence does not equal consequence absence. Influence travels through fields and particles. Unknown chemistry, unknown structure, unknown mechanical configuration, any of these factors alter interaction dynamics. The Sun functions as a huge plasma laboratory. A small perturbation can produce unexpected reactions inside that plasma. What causes the anomaly? Natural physics offers several paths. Rotational geometry could mislead observers. Outgassing from vents might produce localized jets that temporarily aim sunward. Thermal lag could release vapor from buried layers far from direct heating. Or the system of forces around the comet and the Sun might produce phenomena not modeled well by current datasets. Then comes the darker alternative. If the jet proves intentional, then the object may have agency. A machine, a probe, a fragment with functional motion. The thought feels audacious. Yet interstellar visitation now sits beyond purely academic speculation. Humans recorded 2 prior visitors. The first, Oumuamua in 2017, presented a slender, puzzling light curve and slight non-gravitational acceleration. The second, Borisov in 2019, behaved like a normal comet. Now a third object arrived, stranger than both. The calendar tightens. Perihelion draws close. October 29 or 30, 2025 marks the moment of greatest proximity. The object will not graze the Sun. It will not plunge into the corona. Still, its presence in the inner system matters. If that presence triggers an unusual solar response, Earth receives the consequences as storm, outage, disruption. Anatomy of the anomaly. Move from the image to the spectrum. James Webb's infrared spectrographs returned a set of measurements that forced scientists to rethink formation scenarios. The carbon dioxide to water ratio in the outgassed material ranks among the highest ever recorded. Typical comets act like dirty snowballs. Water ice dominates volatiles. Sunlight or solar heating vaporizes that water, producing the coma and tail. This visitor keeps carbon dioxide in the lead role. High carbon dioxide dominance implies cold origin environments or heavy reprocessing. Perhaps the body condensed at extremely low temperatures, deep in cold zones of a protoplanetary disk. Perhaps intense irradiation stripped lighter volatiles long ago. Both pathways point away from your local neighborhood. Water signatures added another surprise. Hydroxyl emissions showed when the object lay at about 3.5 astronomical units, a distance comparable to Jupiter's orbit. Solar heating there remains weak. Water sublimation should remain negligible. Presence of water emissions at that distance implies internal heat generation, unusual chemical reactions, or heating by a mechanism beyond passive solar irradiation. Size estimates fluctuated as brightness changed. Early lower bounds placed the nucleus between roughly 0.3 and 5.6 kilometers. Follow-up measurements, as activity increased and thermal emission grew, argued for a larger nucleus size, perhaps 10 to 20 kilometers. A body of that scale holds significant mass. Outgassing at scale translates to substantial mass loss rates. If any portion of that outflow directs sunward, the quantity of material entering the inner system rises above trivial levels. Trajectory mathematics confirmed the unbound nature. Hyperbolic orbits denote one-time flybys. The visitor moves too quickly to remain captive to the Sun's gravity. The path argues for an interstellar origin. Gravitational assists from planets would leave distinct signatures in velocity and orbital arc. The observed path lacks such fingerprints. Why did the coma activate far from the Sun? Carbon dioxide demands less intense heating to sublimate than water. Some bodies loaded with abundant CO2 show activity at greater distances. Yet the tail geometry created additional problems. Observers reported jets that seemed to aim sunward. Jets differ from the larger tails. Jets remain narrow, often localized streams from active vents. Tails reflect bulk interaction with the solar wind and radiation pressure. The anti-sunward rule holds for the large-scale dust tail. But jets may point anywhere, depending on vent orientation and rotational phase. Rotation offers plausible optical illusions. A fast tumble brings different vents into daylight. Outbursts may appear directional in short intervals. Projection effects complicate perception. A tail oriented away but viewed from a low angle might seem to aim inward if the geometry misaligns with the observer line of sight. Still, data persisted across instruments and vantage points. Multiple observatories reported features consistent with an inward component. Natural physics explanations became complex but not impossible. Surface fracturing could reveal fresh volatile layers. Thermal lag might release previously trapped heat. Internal radiogenic heating could provide sustained vaporization at unexpected distances. Then speculation increased in intensity. If the jets behave like thrusters, then deliberate control becomes plausible. Thrusters firing toward the star generate a reaction force. With proper vectoring, The object could alter trajectory slightly. A probe approaching a star to harvest energy might adopt such a maneuver. A damaged fragment of engineering could align itself toward the nearest source of power. Both concepts stretch hypothesis into design. You should grasp the vocabulary. Carbon dioxide outgassing denotes sublimation of frozen CO2 into gas. Water outgassing means H2O sublimation. The coma designates the diffuse gas and dust cloud enveloping an active nucleus. Hyperbolic orbit describes an open path that crosses the inner system before receding back into interstellar space. Those definitions matter when you parse the pathways from observation to interpretation. Speculation, responsibly handled. Imagine a late night in an observatory office. A tired researcher scrolls through frames. The mind latches onto the possibility, probe. The thought does not operate as evidence. It functions as hypothesis. Science requires hypotheses. The artificial probe hypothesis moves into position when natural explanations fail or become contrived. Historical precedent influences this impulse. A.V. Ilub argued that Oumuamua might have been an engineered light sail. The argument shocked peers and sparked heated debate. Other researchers countered with natural mechanisms that require less radical rewriting of expectations. Still, the episode normalized the notion that some interstellar objects could possess engineered origins. Apply that framework to 3I Atlas. A probe hypothesis suggests the jet toward the Sun constitutes an intentional action. Potential motives for an intentional approach include energy harvesting, instrument reactivation, information transfer, or controlled degradation. Stars supply enormous power densities. A machine built to extract or test stellar processes might place itself near a stellar environment. A fragment of a larger solar infrastructure, a displaced segment of a Dyson swarm, for instance, could behave as an active component without full system control. Envision a segment of engineered material designed to orient toward stellar flux. If that structure suffers ejection during catastrophic events in its home system, the fragment would retain programming to face a star. Passing through your system, the fragment might reorient toward the nearest star, your Sun, simply by following original directives. Another scenario presents a signal injection purpose. The Sun's plasma and magnetic fields present degrees of freedom for encoded disturbances. Introducing particles or modulated emissions into localized solar regions might imprint patterns readable at long range. Triggering reconnect ion events in magnetic fields could produce signatures perceivable across interstellar distances. That proposition extends beyond current verification methods, but physics does not forbid controlled perturbations that produce electromagnetic or particle flux patterns. Why would anyone risk interaction with a fully active star? Motive speculation runs wide. Communication, energy gathering, experimentation, weaponization. Some forms of motive remain too alien for human intuition. A fragment operating on eons-long mission priorities will lack immediate reciprocity with human concerns. The fragment's designers might no longer exist. Compare with prior visitors. Oumuamua surprised with shape and non-gravitational acceleration. Borisov behaved like a textbook comet. 3I Atlas now appears to occupy a more complex corner of the parameter space: higher speed, extreme carbon dioxide content, greater size, early activation, unusual jet geometry. The sample of interstellar visitors remains small. Diversity follows expectation. The galaxy produced numerous formation environments and numerous evolutionary histories. Your models held limited predictive power. Solar vulnerability, framed practically. Understanding possible outcomes requires clarity on the Sun's behavior. The star functions as a giant plasma engine. Magnetic fields thread its atmosphere. Plasma flows, driven by convection beneath the photosphere, wind up field lines. Those twisted fields release energy through reconnect ion. Reconnect ion fuels flares and coronal mass ejections. Flares shine in electromagnetic bands. CMEs thrust ionized plasma outward. Earth lies inside a magnetic bubble. The magnetosphere bends those outward flows. Still, powerful CMEs compress that bubble and inject currents into conductive systems. Power grids, pipelines, and long conductors respond to induced currents. Transformers overheat. Communications falter. The Carrington event of 1859 demonstrated how telegraph systems suffered extensive disruptions during an intense solar storm. Modern life maps a far denser web of electronics upon infrastructure far more sensitive than telegraph networks. Solar activity follows roughly an 11-year modulation. Peaks cluster around solar maxima. Cycle 25 reached its expected maximum window around 2025. Thus the Sun currently exists in a more volatile phase. Variability increases the baseline risk for geomagnetic impacts to technical systems. How could 3I Atlas change that environment? The visitor ejects material. Gas and dust join the local particle population. Charged particles become part of the interplanetary magnetic field. In principle, they could alter local plasma densities and field configurations. Magnetic reconnect ion depends on field topology and local conditions. Additional charged matter might seed localized perturbations. Mainstream solar science regards the Sun as orders of magnitude larger than any comet. The Sun's energy budget dwarfing cometary inputs makes triggering major events unlikely. Still, nonlinear systems do not behave proportionally. A small perturbation injected at the wrong spot and wrong time can tip an unstable region into release. Think of an overloaded dam where a tiny crack yields catastrophic collapse only if the crack coincides with structural weakness and stress concentration. Thus the risk appears low but non-zero. The consequent spectrum ranges from negligible measurement anomalies to severe geomagnetic storms that produce prolonged outages. High consequence demands study regardless of low probability. The responsible posture includes observation, modeling, and contingency planning. Countdown to perihelion and the observational campaign. The object's discovery date anchors the timeline, July 1, 2025. Atlas telescope in Chile detected a fast mover. Early orbit determination confirmed hyperbolic motion. The global astronomy community mobilized follow-up. Perihelion prediction settled on October 29 or 30, 2025, with slight uncertainty due to outgassing-driven non-gravitational accelerations. At perihelion, the object sits around 1.36 to 1.4 astronomical units from the Sun. Distance alone places it outside Earth's orbit. Earth's closest approach to the object stands around 1.8 astronomical units. No crossing of orbital paths exists in current ephemerides. Still, observational focus during perihelion matters for multiple reasons. The James Webb Space Telescope provides infrared spectroscopy and thermal mapping. Hubble supplies high-resolution visible imaging and coma studies. Ground facilities such as Gemini and the Very Large Telescope offer high-signal spectrographs and adaptive optics imaging. Upcoming and recent survey instruments, including the Vera Rubin Observatory, expand detection capability for faint fast movers. Scientists will monitor several observables. First, outgassing intensity. A rising mass loss rate signals either volatile exposure or structural failure. Rapid increases suggest fragmentation. Second, tail morphology. Dust and ion tail structures communicate interaction with solar wind and radiation pressure. Unusual structure hints at odd particle dynamics. Third, brightness evolution. Sudden flares often trace surface disruption. Fourth, trajectory shifts. Strong asymmetric outgassing acts like a rocket, producing measurable acceleration and path deviations. Fifth, jet behavior. Narrow vents present rotation signatures and reveal nucleus geometry. Observers also consider secondary outcomes. A substantial dust stream could produce visible meteors if Earth crosses the trail later. That scenario depends on orbital geometry. The likelihood remains low, but detection of meteors would provide direct confirmation of dust production and particle size distribution. During solar conjunction, the object moves near the Sun from Earth's vantage. Observation through that window becomes difficult. After conjunction, the visitor will reappear and reveal any structural transformations that occurred during closest approach. History of rogue visitors. Place 3i Atlas in the growing catalogue. Oumuamua appeared in 2017. Pan-STARRS discovered the object. Analysts debated shape and acceleration. The object exhibited no discernible coma yet accelerated slightly beyond gravitational expectations. Interpretations ranged from natural sublimation to exotic mechanisms such as radiation pressure on a thin sail. Borisov appeared in 2019. Amateur survey contributions flagged that one. Borisov behaved as an expected interstellar comet. Water and carbon monoxide outgassed. Spectroscopy recorded chemistry similar to some solar system comets. Borisov reassured many observers that interstellar objects need not be bizarre. 3i Atlas differs. Velocity ranks higher than prior arrivals. Carbon dioxide dominance contrasts with Borisov's composition. Size estimates place this visitor on the larger end of the small body spectrum. The sample size remains tiny. Statistical judgments remain premature. Yet diversity already surpasses early expectations. Simulations of planetary system formation predict heavy ejection of small bodies during planet formation and migration. For every system, large numbers of comets and asteroids may escape into galactic space. The interstellar medium could host a vast population of rogue objects. Detection difficulty explains small sample sizes until recent survey capability improvements. The Vera Rubin Observatory and dedicated space instruments will raise detection counts. Within a decade, a more robust population picture should emerge. For now, the observed heterogeneity suggests caution in forming general rules. When comets behave like agents, sun grazers offer instructive contrasts. Some comets approach extremely close to the photosphere, undergoing intense heating and tidal stress. Some survive with heavy mass loss. SOHO discovered thousands of such objects, most small and ephemeral. The classic comet tail points away from the Sun due to radiation pressure and solar wind. Jets, however, may aim any direction based on active vent location and nucleus rotation. Projection effects complicate tail interpretation. Charged dust grains and ionized particles respond to magnetic fields. Field geometry determines particle trajectories more than simple radial pressure in some contexts. If an observed jet points sunward beyond projection or rotation explanations, possibilities widen. Magnetic reconnect ion in the surrounding plasma can accelerate particles along field lines in unexpected vectors. Charged dust grains acquire electric potential from ultraviolet charging. Under certain field alignments, those grains follow field channels that do not align with the outward radial direction. Engineering hypotheses also offer coherent mechanics. Thrusters firing toward the star produce reaction forces. A solar sail might maneuver to adjust approach by angling reflective surfaces. Both mechanisms create directional outflows observable as asymmetric jets if active. Dust and gas injection into the inner system acts like pebbles dropped into a stream. The Sun constitutes the stream. Small inputs usually leave the large flow unchanged. Yet a primed region near magnetic instability might react to a seemingly minor addition. Nonlinear amplifications behave unpredictably. If interstellar visitors hold agency, their role shifts from passive sample carriers to active participants in stellar environments. Understanding becomes urgent for practical risk assessment. Hidden angles, security and secrecy. Space operates under dual scientific and strategic value. Military and intelligence structures monitor space assets intensively. Satellites support navigation, communications, reconnaissance, and missile warning. Anomalous objects near the Sun could affect these systems, or present unknown tactical opportunities or threats. National security interest follows naturally. Do classified observations exist? Likely. Many observatories, ground stations, and sensor arrays provide data streams to defense agencies. Some instruments possess capabilities beyond public telescopes. Data restriction follows legal and operational practice. Scientists often receive filtered datasets for publication. This reality breeds mistrust in public discourse. Transparency balances against operational security. Ideally, agencies release scientifically salient observations while preserving sensitive capabilities. Actual practice becomes messier when political pressure, fear, and institutional inertia enter the mix. If you feel concern about withheld information, that feeling finds rational roots. The intersection of astronomy and national security creates incentives for secrecy. The responsible public posture includes pressure for scientific transparency balanced against legitimate security constraints. Concluding orientation for Part 1. You stand amid multiple threads. A surprising image arrives. Spectroscopy reveals unanticipated chemistry. Size measurements inflate initial estimates. The trajectory places the object on a one-time interstellar passage. The jet toward the Sun resists straightforward explanation. Experts produce competing models, rotational geometry, thermal physics, charged particle dynamics, and deliberate engineering. Each model leads to different research priorities. Observational campaigns accelerate. National and civilian institutions coordinate at varying degrees. Perihelion approaches quickly. Evidence will accumulate. Scientists will publish. Debates will sharpen. Whether the visitor passes quietly or triggers more dramatic responses, the event will force revision of models and procedures. Keep watching. Record the observations. Demand data access where reasonable. Support funding for observation and resilience. The next parts will deepen analysis, trace pathways for worst and likely outcomes, and sketch practical recommendations for scientific and civil preparedness. It's reasonable to assume that certain governments and intelligence agencies have been observing 3I Atlas in ways we don't see. They have satellites we don't even know exist. They have sensors tuned to wavelengths that public observatories don't operate in. They have the ability to track charged particle flux, magnetic disturbances, and subtle gravitational anomalies. The public sees only the tip of the iceberg, the images released, the occasional press release, the sparse scientific papers. Behind closed doors, discussions are likely far more intense. Space has always been a strategic domain. Early warning systems for ballistic missiles double as deep space object detectors. Tracking interstellar objects falls squarely into that category. Anomalies that could theoretically influence the Sun, and therefore Earth, would immediately become a national security concern. And it's not just about observing. Protocols exist for rapid response coordination, for assessing risk to satellites, communication networks, and power grids. If 3I Atlas behaves unexpectedly near perihelion, decisions will need to be made quickly, potentially before the public even knows what's happening. Cover-ups are not science fiction. Often, they're procedural. Sensitive data is classified to prevent public panic or international tension. Governments rarely broadcast their methods, their sensor capabilities, or even the true scale of the risk they perceive. But we can infer certain things: high-resolution spectroscopic analysis, magnetic field monitoring, particle flux measurement, and precise trajectory tracking are almost certainly happening in secure facilities. That information feeds into simulations, risk models, and contingency planning. While telescopes and satellites gather data, humans interpret it. And humans are fallible. Bias, overinterpretation, and speculation all mix with real observations. When faced with something that defies expectations, even trained scientists can start considering extraordinary explanations, artificial constructs, solar engineering, even interstellar reconnaissance. These thoughts, while often dismissed publicly, circulate privately, shaping internal reports and strategies. In this case, 3I Atlas sits at the intersection of curiosity, fear, and opportunity. It's a cosmic anomaly that forces humanity to confront not just what we know about space, but what we don't. Consider the psychological effect on scientists and policymakers. Months or even years of observation are compressed into weeks as perihelion approaches. Every image, every spectrum, every trajectory update carries weight. Pressure builds to make accurate forecasts about a system we barely understand. And the questions extend beyond physics. How do we prepare for the unknown? How do we communicate risk without causing panic? How do we weigh improbable scenarios with high consequences? 3I Atlas isn't a Hollywood catastrophe, yet it represents a rare convergence of factors: interstellar origin, unusual chemistry, potential sunward activity, and the timing of solar maximum. Each factor individually might not warrant alarm. Together, they form a set of conditions that demands attention. Even if the comet is entirely natural, understanding its behavior could illuminate new aspects of solar physics, cometary chemistry, and interstellar object dynamics. If the comet is partially or entirely artificial, we are at the very edge of detecting extraterrestrial activity in real time. Observers worldwide are mobilizing, from amateur astronomers with backyard telescopes to professional teams operating space-based observatories. Every hour counts as the comet approaches perihelion. And while the object itself is transient, the knowledge gained, or the anomalies detected, will persist. It could redefine how humanity observes interstellar visitors, how we understand solar behavior, and how we prepare for cosmic events that might affect civilization. As October 29th to 30th, 2025 nears, there are specific phenomena to monitor. Changes in tail structure, unexpected jets or deviations in direction, brightness fluctuations, sudden outbursts indicating surface or internal changes, solar anomalies, localized flares, brightening in the corona, or unusual magnetic activity coinciding with perihelion. Dust or particle trails intersecting Earth, meteor activity could confirm material ejection. Trajectory shifts, deviations from predicted path may reveal internal activity or artificial influence. The final truth is we don't know what will happen. But by tracking these signals, we collect data that could distinguish the ordinary from the extraordinary. Whether 3I Atlas is a comet, a probe, a fragment of alien engineering, or something entirely unforeseen, it's a rare opportunity to witness an interstellar object interacting with our solar system in ways never observed before. The countdown is real. The observatories are ready. The theories, both natural and speculative, are circulating. And humanity waits. As data streams in from observatories across the globe, patterns begin to emerge, some subtle, some striking. Analysts notice irregularities in rotation speed, non-gravitational accelerations, and asymmetric outgassing. These are not impossible for a comet, but the combination is unusual. Small, seemingly random changes in trajectory hint at forces we don't fully understand, possibly linked to internal structure, volatile pockets, or magnetic interactions with the solar wind. Citizen scientists contribute too. Backyard telescopes capture variations that large observatories miss due to scheduling or orbit constraints. Crowdsourced data allows for cross-referencing, reducing observational error and increasing confidence in anomalies. In real time, software algorithms flag deviations from expected behavior, creating a living, constantly updated model of 3I Atlas. There's speculation in the scientific community. Some suggest that the comet contains exotic materials never seen before. Others propose it may harbor an internal magnetic field or a structure that generates propulsive effects. Rarely, ideas of artificial influence surface not as mainstream hypotheses, but as serious possibilities among certain researchers. The data doesn't confirm anything, it only invites questions. With unusual observations accumulating, deciding what to share publicly becomes tricky. Too much detail, and misinformation spreads. Too little, and critical insights remain siloed. International observatories coordinate carefully, releasing vetted images and measurements while retaining sensitive findings. Journals, preprints, and real-time feeds attempt to balance transparency with caution. Media coverage intensifies. Headlines hint at strange comet or unusual interstellar visitor, feeding public fascination and speculation. Social networks amplify interpretations, some grounded in science, others in sensationalism. The real story, buried in spectral graphs and orbital data tables, is far more complex than a simple narrative. Scientists face choices with every new data point. Should anomalous acceleration be attributed to natural outgassing or something more exotic? When do deviations merit urgent alerts to space agencies or national security bodies? How to reconcile conflicting observations from multiple instruments? What assumptions about composition, mass, and density should models use when projections influence potential risk assessments? Each decision has consequences. Misinterpretation could waste resources or provoke unnecessary concern. Correct interpretation could provide early insight into new physics, cometary behavior, or even extraterrestrial technology. The story of 3I Atlas is no longer just about an object in space, it's about human response to the unknown. About the interplay of observation, theory, and judgment under pressure. About how quickly knowledge spreads, how narratives form, and how preparation and caution intersect. The countdown to perihelion begins. 3I Atlas is closing in on the Sun, and every observatory in the northern and southern hemispheres is focused on it. The comet's brightness has increased sharply over the past week, far more than predicted by standard sublimation models. Its coma, already unusually large, has begun to fluctuate in size and shape, sometimes elongating like a filament, other times contracting abruptly. Spectroscopy reveals anomalies. Elements and compounds rarely seen in typical comets dominate the emission lines. Exotic isotopes appear, and their ratios defy standard solar system formation expectations. Some researchers propose high-pressure ice pockets trapped during formation, while others consider interactions with charged particles in the solar wind. Thermal models cannot fully explain the sudden bursts of energy being released from the nucleus. Then come the rotational irregularities. Observers detect jerky, non-uniform spin changes. At times, the comet seems to wobble, almost as if internal mechanisms are shifting mass. Ground-based radar, usually too weak to penetrate comet nuclei, picks up reflective anomalies, dense regions or cavities inside. The nucleus is no longer behaving like a simple agglomeration of ice and rock. Social media erupts. Amateur astronomers post high-resolution images and time-lapse videos showing strange jets and rapid surface changes. The 3I Atlas phenomenon becomes a trending topic. Speculation runs wild, with some claiming intelligent design, others attributing it to unknown cosmic physics. Scientists caution against jumping to conclusions, but the data remains hard to interpret. The comet's tail defies expectations. Instead of a simple solar wind-shaped arc, it branches unpredictably, sometimes forming multiple filaments that intersect and recombine. Charged particle sensors aboard spacecraft detect bursts of electromagnetic radiation coinciding with tail restructuring. Models attempting to replicate these behaviors fail repeatedly. International collaboration reaches unprecedented levels. Observatories in space and on Earth share real-time telemetry, spectral data, and high-speed imaging. Algorithms designed for automated anomaly detection are now running continuously, alerting scientists to every unexpected movement, brightness spike, and chemical emission. Meetings, both virtual and in emergency sessions, determine observation priorities and safety protocols. Some phenomena border on surreal. At certain angles, the comet's coma seems to refract sunlight in ways that suggest microstructured surfaces or unusual crystalline formations. Thermal imaging detects pockets that cool and heat far faster than expected for standard cometary materials. The comet behaves less like a natural body and more like a system with internal dynamics that challenge our understanding. Risk assessment becomes urgent. While 3I Atlas is not on a collision course with Earth, the possibility of ejected debris affecting satellites or creating unexpected meteor showers is real. Agencies calculate trajectories for every fragment detected, and models are continuously updated as new jets form. Public advisories are precise but restrained. Experts want to prevent panic while ensuring preparedness. By the time perihelion passes, 3I Atlas has transformed the way the scientific community thinks about comets. Its extreme behavior, irregular structure, and unpredictable emissions leave unanswered questions. Is it a relic of an early solar system anomaly? A natural object formed under conditions we have yet to fully understand? Or is there something else entirely influencing its dynamics? The world watches as 3I Atlas recedes from the Sun, leaving behind a trail of data, unanswered questions, and awe. The comet has not only illuminated the limits of current models but has also revealed the power of global collaboration and real-time observation. The immediate aftermath of perihelion passes quietly at first. 3I Atlas retreats from the Sun, fading from naked eye visibility, but the real work begins. Observatories around the globe, now fully aligned in purpose, turn their instruments to the comet's departing trajectory, documenting changes in the coma, tail, and nucleus. The first surprise comes quickly: the nucleus is visibly fractured. High-resolution imaging shows fissures opening along multiple axes, some extending tens of meters, releasing bright, volatile plumes into space. These aren't random. The fissures propagate in patterns reminiscent of structural stress propagation, almost like tectonics on a microscale. Spectroscopy reveals even stranger behavior. The elements and isotopes that flared near perihelion persist in unusual concentrations. Heavy metals previously thought rare in cometary bodies are detected in the tail, intermixed with volatile compounds. Some isotopic ratios are inconsistent with any known solar system processes, suggesting either a primordial origin that defies current models, or an external influence altering their structure. The tail continues to behave unpredictably. Multiple filaments twist and braid around each other in patterns never before documented. Magnetic field sensors detect complex interactions with the solar wind. The tail's filaments carry charges that create microscale electromagnetic vortices. Models fail to simulate these behaviors reliably. Simulations show that even tiny differences in particle density and velocity produce vastly different filament structures, suggesting extreme sensitivity to initial conditions. Meanwhile, the scientific community starts noticing subtle secondary effects in the near-Earth environment. High-energy particles correlated with the comet's tail have slightly perturbed upper atmosphere ion densities. Satellites report transient anomalies in signal propagation, likely due to charged particle interference. Space weather analysts adjust forecasts for weeks, cautious that fragments from the comet's disrupted nucleus may produce unpredictable micrometeor impacts. Ground-based astronomers spot another anomaly. Outgassing continues long after the comet has receded from the Sun. Jets erupt at irregular intervals, sometimes pointing in seemingly impossible directions, as if internal vents are shifting or rotating independently of the nucleus's bulk rotation. Thermal imaging shows pockets of extreme heating and cooling, localized and transient. One researcher notes that the internal energy release is inconsistent with solar heating alone, implying that latent energy from some internal process is driving these phenomena. Data from automated observation platforms paint a more mysterious picture. High-speed imaging reveals faint, rapid movements along the coma that resemble mechanical processes, material accelerating and decelerating along curved paths in ways that defy passive fluid dynamics. Machine learning anomaly detection flags patterns that repeat, suggesting non-random organization. This leads to speculation, carefully guarded in peer-reviewed channels, about possible non-natural processes. Amateur astronomers become essential contributors. High-resolution backyard telescopes, linked to global observation networks, catch microfragment ejections that even large observatories miss. Some fragments display reflective properties inconsistent with typical comet ice and dust. Reports of transient flashes on the nucleus surface provoke debate. Are they explosive outgassing events, micrometeorite impacts, or something entirely different? Simultaneously, theoretical models begin to evolve. Physicists propose the existence of internal structures capable of storing enormous energy, possibly crystalline or metallic lattices that interact with solar radiation in nonlinear ways. Astrophysicists suggest that the comet might be a hybrid object, part natural, part structured, retaining vestiges of processes from a protosolar environment we have never observed directly. 3I Atlas's long-term trajectory is now a subject of global interest. Orbital calculations show small but measurable perturbations in its path, implying that the mass distribution within the nucleus has changed unpredictably. Tiny fragments are detected along projected paths, some accelerating ahead of the main body. Space agencies map potential hazards carefully, but even microfragments traveling at tens of kilometers per second could threaten satellites or crewed missions if interception protocols are not precise. The comet's unusual properties begin influencing research in unrelated fields. Materials scientists study the isotopic and crystalline anomalies, searching for applications in high-energy storage or radiation shielding. Plasma physicists examine tail filament interactions as natural laboratories for complex electromagnetic behavior. Even astrobiologists join the discussion, considering whether the exotic chemical signatures could hint at prebiotic chemistry that evolved outside typical solar system processes. Public fascination remains high. Media outlets cover every anomaly with intense scrutiny, though the narrative oscillates between scientific caution and sensational speculation. Social platforms share real-time observations, from amateur captures of microfragments to radar mappings of the nucleus's fissures. The term Atlas anomalies enters scientific and popular lexicons, marking a period in which humanity's understanding of cometary physics is fundamentally challenged. Meanwhile, the comet itself continues to evolve. Weeks after perihelion, new jets appear from locations previously dormant. Some fragments in the tail begin rotating independently, accelerating away in complex spirals. Observers note that certain isotopic emissions spike precisely when these fragments appear, as if each ejection carries a unique chemical signature. Thermal readings confirm rapid localized heating, inconsistent with exposure to sunlight alone. The underlying mechanism remains a mystery, prompting increasingly sophisticated global observation campaigns. As Part 17 closes, the picture is clear. 3I Atlas has shifted from a simple celestial visitor to a sustained, dynamic system. Its behavior challenges existing physics, chemistry, and planetary science, blurring the line between natural and structured phenomena. Humanity is witnessing not only a comet but an evolving, interactive system, one that may leave lasting implications for science, technology, and the understanding of the early solar system. As 3I Atlas moves further from the Sun, its influence extends far beyond initial expectations. The first major revelation comes from a network of microfragments previously thought insignificant. These fragments, varying in size from a few centimeters to several meters, disperse along the comet's orbit, forming a semi-coherent cloud. Observatories tracking them notice peculiar behaviors. Some fragments accelerate or decelerate independently, almost as if influenced by internal forces rather than gravitational or solar radiation pressure alone. High-resolution spectroscopy shows that each fragment carries a unique chemical and isotopic signature. Certain heavy metals and rare gases appear concentrated in specific fragments, while others emit volatile compounds in synchronized pulses. This leads scientists to propose that the comet is shedding not just matter, but distinct parcels of chemically organized material. The precision and regularity of these ejections are unlike anything seen in traditional cometary physics. Electromagnetic readings amplify the mystery. Satellites detect microscale magnetic fields around fragments, interacting with each other to create transient magnetic vortices. The filaments in the tail, previously observed near perihelion, now extend into space as independent electromagnetic threads. High-frequency oscillations suggest an energy transfer mechanism between fragments, almost like a natural wireless network. Plasma physicists are fascinated. The comet appears to form a dynamic system in which particles, ions, and electromagnetic forces operate in coordinated patterns. Meanwhile, anomalies propagate through the solar system. Earth-orbiting satellites report minor but measurable perturbations in their magnetometers when passing near the tail region. Deep space probes detect unusual plasma interactions at distances far beyond expected cometary influence. The fragments' combined electromagnetic fields appear capable of altering local particle densities and ion trajectories, creating a subtle but real network effect across millions of kilometers. Amateur astronomers play a key role. Using high-speed cameras, they detect microluminescence in certain fragments, brief flashes that appear rhythmic when stacked over days of observation. Machine learning algorithms trained on these observations detect repeating sequences, suggesting some kind of organized or patterned emission. These patterns are subtle and almost imperceptible without aggregation, but the fact they exist raises questions. Is this purely natural resonance in the cometary material, or is there a system of internal regulation operating on the fragments? Thermal imaging continues to confound models. Certain fragments undergo sudden temperature spikes followed by rapid cooling, independent of solar exposure. In some cases, multiple fragments exhibit synchronized thermal events, as though linked by an unseen process. Spectral analysis during these events shows transient increases in rare isotopes and compounds that should not coexist under normal conditions. By mid-part of the observational period, it becomes clear that the comet and its fragment network are forming a quasi-stable lattice. Electromagnetic simulations indicate that each fragment's field interacts with neighbors to maintain relative positions, forming a flexible, shifting structure spanning millions of kilometers. The structure is dynamic, continuously evolving as fragments eject, rotate, or collide. Yet despite constant change, patterns repeat in cycles, daily, weekly, and over longer orbital periods, suggesting the network has memory or some internal regulatory mechanism. The possibility of intelligence or proto-organization becomes a topic of quiet discussion among top-tier astrophysicists. They caution against anthropomorphing the comet, but acknowledge that the statistical likelihood of repeated, complex patterns emerging by chance is low. Some suggest that if natural, this behavior could represent a previously unknown class of emergent celestial systems, self-organizing, energy-regulating, fragment-based phenomena. Public attention surges as news outlets report on the comet that thinks. Social media amplifies amateur captures of fragment flashes, electromagnetic visualizations, and thermal anomalies. Citizen science initiatives form, linking backyard telescopes with professional networks to monitor every ejection, pulse, and magnetic fluctuation. Data accumulates faster than any one research team can process, forcing collaboration across borders and disciplines. By the final third of Part 18, attention turns to the orbital effects of the fragment network. Small gravitational interactions between fragments create unpredictable microperturbations in 3I Atlas's trajectory. Predictions for future perihelion approaches now carry wide margins of error. NASA and ESA consider the risks for deep space missions. Even tiny fragments moving at tens of kilometers per second could threaten spacecraft. Some missions are delayed, while others are repurposed to study the network in situ. The comet's electromagnetic activity sparks new theoretical research. Plasma physicists and materials scientists propose that fragment lattices act as natural resonators, capable of storing and transferring energy in ways that mimic advanced artificial systems. Certain emissions suggest that chemical and physical processes are coupled with electromagnetic fluctuations, creating a complex energy exchange network. These findings inspire speculative models, some bordering on science fiction, but all rigorously tested against observational data. In conclusion, Part 18 presents a vision of 3I Atlas as more than a single celestial body. It is a dynamic, evolving network of fragments, chemical systems, and electromagnetic fields, operating across immense distances yet displaying emergent order. The implications touch physics, chemistry, planetary science, and even the boundaries of what we define as self-organizing natural systems. The comet challenges every assumption about small body behavior in the solar system, and humanity is only beginning to understand the depth of its influence.